Today we'll review chapter 1, Introduction. This is a review of the whole chapters for a course EL 4242 and the power electronics. This is for a power electronics course, a review of introduction on chapter 1 on introduction. And this is basically we'll go our overview of the whole chapters. And I expect before you review these chapters, I strongly recommend that you at least go through the video for the worked out examples in the book. And there are a lot of worked out examples in the book, and there is a video there, and I would encourage you to use these mathcat files. You don't have to do anything. This is on the UWF desktop. You just run the program, download in your computer, run the program. There are some video how to use that, and I expect you to at least review these videos for worked out examples, and then review the chapters. And then this is the first is very important to know that the power electronics deals with the switching of a power semiconductor device, like basically it's an electronic device like any of the electronic device. And this is you let us consider is a switch, like a RL is the load, and this is the DC battery, and then you have a switch. This trace could be performed by any of the semiconductor devices. There are different types of semiconductor devices, and then there is a gate voltage or gate pulse you applied. Now then what happened that when you have is normally this switch is normally with the arrow with the direction is giving that the current will be a unidirectional current. This is normally a VCC, it's a DC voltage, and then it's a ground. Now what is happening now, once you apply a gate voltage, like once you apply a gate voltage you apply to the switch, this is the gate voltage you apply, like put a pulse there. Now once you have a pulse, then you expect, depending on the switch, there will be a current through that switch flowing from the gate, current flowing through the switch. And now once you have a gate current flowing through the switch there, now what will happen that the switch will turn on, but in real life the switch will not turn on right away. There will be delay time. There is called the delay time when the switch started, and then from the delay time the voltage will as the current rises, the voltage across the switch will fall slowly. At the beginning, when the switch was off, you have the whole supply voltage was across the switch. Slowly current will rise and the voltage will fall. This is the typically practical devices, but theoretically it will be instantaneously. There will be a delay time, there will be a rise time, and then the device will be completely on. When it is completely on, there will be a voltage, finite voltage, like a saturation voltage of the switch. And if there was the ideal switch, it will be 0 voltage, and then the maximum current will flow. How much current will flow? VCC divided by the VCC. The current will be like maximum will be VCC divided by the RL minus, there will be a drop here of that saturation voltage, will be V of the switch saturation voltage, because there will be small voltage that the maximum current will flow, the switch current will flow, whatever the supply voltage divided minus that the drop across the switch will be saturation voltage. That's the maximum current will flow through that, and that current will flow there. Then now there are issue when this is a when they turn it off, when you turn it off, then the device will not respond right away. There will be, it's called the storage time, because these are semiconductor devices. To turn off, it needs certain time to combine or recombine the charges of the devices P and the electrons and holes. There will be a storage time. That means the delay time, rise time, this the on time, actually on time, this is the storage time, and then fall, and then this is the off time, keep the switch off. This is the typical one. Now with the voltage and the current, like if you want to look for the power across the switch, there will be V and I multiplication. If you do that, there will be a power. It will be like something like this, sort of a sine wave, and then you can find out if this current is rising linearly from the minimum to the certain value, and the voltage is falling linearly, you can find out it's a linear the rise. You can find out the expression for the voltage and current. If you multiply that, that will be the power. Then normally the power becomes maximum power, instantaneous power become really somewhere in the middle of that. But the steady state power, which is the V, which is a small, and then I. The V of the switch, the V of the switch is very small, which will be time the maximum current, that become a very small, the steady state power. Now this is the typically of that any switch. The question comes, is this, the voltage will be DC, what will be the current there, how much will be the power there, and these are the things you ask for. And then depending on the switch, whether it is a bipolar or MOSFET, that the different issue will come there. Let us go through them. Now the question comes for a semiconductor device is what? Semiconductor device is like a p-n junction. You got a P and an N junction. If we apply a voltage across the switch, small voltage, typically VD is like a 0.7 roughly, the device will be on, or you can put a resistor to limit the current. That means once it got a voltage, it will be turned on itself. Now, is it a control device? No. Is it a control off? No. And then it's a bipolar? No, it's a unipolar device on one. That means that none of the above is the question there. The diode is a semiconductor device, but it's not, you cannot turn on, you cannot turn off, and it's not a bipolar is a unipolar device. That's the answer for that one. The next one, silicon control rectifier. It is a device. You got say NPN P or NPNP. This is the device you have. Like this characteristic of the device, silicon control rectifier, you can turn on by small. You can turn on. Once it turn on, it becomes like a diode. It's a control device. You can turn on, but diode you cannot control. Once you turn on, you cannot turn off. That's the characteristic of the device. This means you cannot turn off. You can turn on, yes, and you cannot turn on. This is the only thing answer. The device is a turn on device, which is the answer, correct answer. Now SCR requires what type of path, but the beauty of the silicon control rectifier, you apply a small pulse. Once you apply a small pulse to the gate of the device within itself, it latches itself, and after that, when you take the gate pulse out, it will remain on. That's the latching device. That means that the device requires a small pulse to turn it on, and then you don't need a continuous pulse, because if you give it, you can give it, but it's not going to have any effect because you will lose power, the gate power there. The answer is the small gate pulse is required to drive to turn on, and you cannot turn it off. Okay, you cannot. You don't require a continuous pulse. Like gate turn off tarifier, that's the gate turn off tarifier. Is another device you turn on with a gate pulse. You can give a negative pulse to turn it off. That is the turn on and turn off. It's a gate turn off. You can turn off by itself. That's why it is a turn off device and it's a turn on device, and all of them. There's both there. Now, is a bipolar transistor. If you remember a bipolar transistor, if you remember a bipolar transistor, and the transistor, the bipolar transistor will have you got an NPN device. NPN device. That means that bipolar transistor is a turned on by applying a gate voltage, or a base current. It's a base current basically. You apply a voltage to the base, which produces a base current, and then it turns it on. And now you can turn on, and then by turn on, but you can turn on and you can turn off by taking the base drive off. If the gate pulse off, it will be turned off. That means you can turn on, you can turn off, but it requires a continuous gain current. You can turn on, you can turn off, and then you can control the current by basically it's a current dependent. If you apply base current, then the collector current depend on this. All of them. Current control device is a turn on device and turn on device too. Okay. Now let us see the next question asked of BGT requires what type? BGT requires that as long as you turn on, it will remain on. If you take the gate drive or base drive off, it will be off. That means you have to apply a continuous gate pulse. It is a continuous gate pulse. If you give by a thyristor, you pulse a small pulse, it will the latch. It's not a latching device. That's why it's a continuous. You need to get a continuous gate pulse. Like MOSFET is a MOS by itself. It needs a voltage to turn on, not a current. You need a small voltage to turn on the devices, and it's a voltage dependent device. We apply a voltage to the gate, to the source, and then device will remain turned on. If you got to turn on, then you got the drain current. Okay. Now this is the control turn on. You can turn off too. It is a control turn on. It is a control turn off device, and it is a voltage control device. It's a voltage dependent. You can say voltage control or voltage dependent device. Okay. You apply a voltage to the gate, to the source, and then the drain current depends on that voltage. Okay. That means all of them. But let us see the next one. The IGBT is a combination of the bipolar and the MOSFET. If you look through the output side, it is like a bipolar. It has a collector and an emitter. It got a collector, you got a collector and emitter. I don't want to touch this one. If you look through that, it's a collector, and there's an emitter, and this is the gate there. If you look to the outside, it's a bipolar device. But if you look to the gate, it is like a MOSFET. It's a mixture or the blend of the MOSFET and the bipolar. It uses the best or advantage, whatever the advantage of the bipolar and the MOSFET, you combine that. It is you can turn it off, and you can control it, all of them above. It's a control device. You can turn it on, it's a turn off. You can control turn off, and also it's a voltage control device, not a current there. It's easy to control the current voltage than the device. IGBT requires what? IGBT requires a continuous gate pulse. Remember, like a MOSFET, if you take the gate pulse off, it will be off. It requires a continuous gate pulse to turn it on. If you give a small pulse, it will turn off. If you give a pulse, it will turn on and off. If you try to give this, if you give a on and off pulse there, it will be turn on and turn off, and it will be like this. But if you want to remain on continuously, or as long as you want, it will be continuous gate pulse. What is the I square T of a semiconductor device? You have to, like a normal fusing. Normal fusing, you use a fuse. But if you use a fuse, then that fuse, it takes the time to blow it off. But what happens in a fuse? You apply a large, and if you exceed a current limit, that current will be, there will be fuse will have a resistance, there will be a current, there will be I square R, is a power. That power will create create a heat, and that heat will melt the fuse. That's what happened. But in semiconductor devices, they use those special type of fuses so that the I square T of the device, I square T of the devices, each is like, and the fuse will blow. The I square T of the fuse has to be lower, and is the higher than the I square T of the fuse, so that fuse will blow, not this device there. Now what it happens that the energy, if you look to the energy of the I square T I square time the dt, the time, the energy, what is an energy? The power is the I square R is the power, and then you integrate with the time, and over a time, that will be like, this will be the average over a time, or an average power, and then integrate that, the power over a time interval, that gives the energy there. That means the I square T is a measure of the energy of the fusing protection, is the I square R, because I square R is represent I square is the power, and the time bring the power time, that the time, power times the time, it gives the energy. That means the I square T is a measure of the energy required for the fusing. That this is not the power requirement of the protection; it's the energy requirement. It's the energy represent the energy, not the power. Now, if you look through the capacitor, the current through a capacitor depends on what? Like we remember that current of a capacitor is C dV by dt. See that? That means that current of through a capacitor depends on the dV by dt. Okay, the answer is dV by dt of its voltage, not the di dt. Okay, if you look through that, the voltage of an inductor is will be equal to L di dt. If the question was asking for that inductor depends on the L di dt, but for capacitor is the dV by dt. And that is this, the answer is that the current flowing through a capacitor depends on that dV by dt. And that question comes to the important because normally semiconductor devices would have you have a device, maybe a diode you have. Even a diode, internally there is some junction capacitance. If they go, we'll talk later on. If you got a junction capacitance, if you go have a switch, if you have a switch there, if you have a switch there, you put a resistance there. If you got a switch is there 10 volts here, and suddenly you turn the switch, the device has no voltage. Suddenly you turn on, there will be suddenly this device will see a certain voltage there, and then dV by dt will be large. As a result, there will be a current will going through this the junction of that, and the capacitor is going to destroy that. And the surge of the current will go. The current will go through the capacitor depends on that, the dV by dt, because you have a switch, there was no voltage, suddenly you turn on the switch like a plug on, this, turn on the switch, and the voltage was 0, suddenly you go from 0 to 10 or 0 to 100, that dV by dt become very large instantaneously, and there is a device, semiconductor devices, there will be junction capacitance inside or internally, that as a result that there will be internal current flow to those through the junction, and it will destroy the dV. That's very important to know, that the current through a capacitor depends on the dV by dP, that concept. Now, there are in a power electronics circuits, normally you deal with this, the current. Sometimes the current is DC, sometimes it's alternative, or a mixture of DC and alternative. There are different shapes of current you go, because once you have a pulsing that waveform, and the shape of the current depends on your load, and so on. So this book has some of the commonly encountered one. Please review them and give you how to find the two currents. One is the RMS current and the average current and the duty cycle, and review them. There are some questions, if somebody asks you some questions about that. One of the question, what is the RMS current of that one? If the peak value is given, if the peak value is given, and then you can find out the RMS value by 2, because you know that this is if you know the root mean square value of a sine wave is the peak divided by root 2. But here, where this is same, it's not a sine wave, but it's a pulsating wave, because the root mean square value is the root of the mean of the square. The root of the mean of the square. Root of the square, you take this to mean of the square, I square root of the mean, and that's they take this one, root of the mean of the square. If you take the square root of the negative or positive, if this was like the negative, it doesn't make much difference, because the negative of the half negative of a half sine wave is the square of them is a positive. That's why it doesn't matter whether this is a positive negative of a sine wave, or these two are all positive pulses. This will be the peak value. If somebody is giving the IP, you should be able to calculate that. And if that peak value is like IP is 10, you can find out what is the RMS value. Okay, that I expect you should be able to do that. Now, what is the RMS value of this waveform? This is only not all of it is a part of it. Like this is not a half sine, but it's a part of that. You can find out duty cycle. What is the duty cycle? Or what is the total P, and half of that T by 2, and you can find out the RMS value of this count. And if this is given like if the duty cycle is 50% and then current is 10, you should be able to find out what is the RMS value of this current shape like this. Okay, and this is a simple answer. Now, RMS of this pulsing waveform. This is a pulse waveform RMS value, and then this will be the duty cycle. It will be square root of that. If the duty cycle is 50%, you should be able to about how much is the duty cycle RMS value of this current. Like what is the average value of this waveform? If you make an average value, if you get average value, it will be simply I average will be equal to K times the IP. Okay, but this will be the average. Okay, average will be half somewhere that depends on the duty cycle. And this is the one you should be able to calculate. Now these are these we mentioned to the beginning there. Like you see that if I look to the waveform, the total period of this cycle, it has to be every time you turn on a practical switch, there will be delay time, there will be rise time, you've got really actually devices on, there will be storage time, there will be fall time, then actual off time. If you turn on and off within a certain frequency, there is something to look for. The total frequency will be TD, TR, the total on time, storage time, off time, actually off time there. Now if they ask you that the values are given right, the on time, and then you can see that the TO is on, you can find out what is the maximum frequency operation. That's the limit for each devices you're looking for. Manufacturer, if you look to the data sheet, manufacturer will give you those parameters that give you the maximum frequency limit. Ideally, one would like to have a switch or a device which will operate infinite frequency, but it's not. That's why if the question asks for you, you should be able to find out what is the maximum frequency of the particular device. And if an example give you that these are the values, what are the maximum of a particular switch or a device, what are the maximum, you should be able to find out that. And that's the now if somebody asks you that the load resistance, is the unidirectional switch is now question come here, do you need the load resistance? That's the question. It's a common sense. Do you need the load resistance? Yeah, we need. Otherwise, what will happen if you don't have any load resistance? Look at that. If you don't have any load resistance there, if you turn on the switch ideally will be very small voltage. If you got 100 volts here, that the current will be almost like infinity, and that you need a load resistance to limit the current. You need the operation of the circuit, good operation to controllable circuit. Otherwise, that's not practical. The answer is needed for the operation of the circuit. The next question calls for voltage source. Now the voltage source should be is a main supply. There are two voltages there. One is the gate pulse, is the pulsating voltage or the gating voltage, or you can say the gating voltage or the signal voltage. Different way you can define. But the main source for that is VCC. Like the answer is VCC, the main supply voltage. It's a DC supply, or you can say that. Okay. Then now if you look at the voltage shown in figure is a main supply voltage or switch control. This VG is that it's not the voltage, but it's not the main the DC voltage, or this is the switch or control switch voltage. You can say the control switching voltage, okay, or the switch control voltage, whatever or you can sometimes you'll call it gate voltage. But it says the VG, you specify the VG is that switch control voltage. Now the control switch. Now in this particular case, the switch is unidirectional switch. It is a voltage control switch. It is shows as it is a unidirectional control switch. Current has to flow through that, and the switch is like a controlled by the voltage, that voltage control switch, and it's not a current control switch. The current as shown is a unidirectional switch. It's a voltage control switch. The ideal characteristic of this, what will be the ideal characteristic? It should be low on state voltage. When the switch is on, that voltage should be very, very low, and then it should be able to taking a high current through, and it should turn on fast. They should have all of them. It should have a low on state. When you switch on the device, it should be no voltages. When you put a current, you should be able to as much current as you like, and it should be fast to turn it off. Okay. Also, another criteria is not there. When you turn on, it should turn on instantaneously. It didn't a question ask for that. Increase in resistance. If you increase the resistance, what will happen there? If you increase the resistance, like the device current, this device, the drop across the device, normally if you remember is simple diode. These are all when the device is turned on, it's like a small like a diode. Okay, it's like a diode there. If you have a more current, the drop becomes larger. The drop becomes a it become a larger. If you more current through that, if you got a more current, there will be a more the on-state drop. That means increasing the resistance, load resistance. If you increase the resistance, that the increase in load resistance means the current through it will be less. If the current through it is less, that means that the on-state switch current, the current will be low. It will decrease. If you increase the resistance, it will decrease the switch current. It's obviously Ohm's law. Now, on-state voltage. The higher on-state voltage will increase the on-state power loss. Of course, if the switch has if this voltage across the switch is, depends on the device. If this is a 0.2, 1.3, 1.44, if your on-state voltage is high, the power losses will be high too. The power is equal to the voltage times the current. If this, the voltage is saturation voltage is large, for the same amount of current, the power will be the high too. Now, the voltage source VCC, in this particular case, it's a DC supply because it shows it is, the unidirectional. But that if you got a DC or AC, if you apply AC, the switch, most of the switch cannot handle those, the AC there. That means that will be unidirectional. Let's say the unidirectional. That means only one direction can kind of flow there. If you apply in the AC voltage, the current will try to flow in both directions. But as it says that the current can flow only one direction, that means the source must be a DC source. DC must be source. Okay. Now the gate voltage should be, it could be a DC or pulsating DC. There is a difference. This DC is a pure DC, okay, or pulsating DC is zero. This is a pulsating DC. It could be pulsating. This is still zero. It's a pulsating DC. It's not an AC because normally the gate signal is not an AC, and then it's not a DC or AC. It is a pulsating DC. It could be DC or a continuous DC, or it could be pulsating, just like by as silicon control rectifier. It could be pulsating, just putting the pulse there. Then the current switch, if this is switch, like if this is going there, this is a particular example. If the Vs is given, the supply is given, and this is 0, okay, the 0, and that current switch is limited to 1 amp, and the current will be equal to, you are limiting this current to 400 amp, and you should be able to find how much of the resistance will be, like what will be the resistance greater than that. I expect you should be able to calculate that, right? And if the VC is 200, the voltage is 0, how much limit the current to 400? That means what will be the resistance higher than certain value. We should be able to find out. Okay. Like power dissipation, ask for your the peak power dissipation is happens once. The peak power happens obviously from there when the switch transition goes on. The switch transition from one state to the other one, either from on to this, off to the on, or on to the off, that becomes transition time, the peak power happens. There are some examples in the book. I would ask you to, I encourage you to review them. The on-state power, what is the on-state power? You should be able to find out that if this is the VCC is at 200, and then this is the 1 volt, this is the 1 volt, and this is the 100, the R, you should find out how much the current flowing through that, right? You can find out how much the current flowing through that, and once you know the current through that, you can find out, the current, the voltage, you can find out how much a power. You should be able to calculate it out, on-state power. This is the on-state power somewhere there. This is the power you're talking of. The current, and the current, and this is the current, this is the voltage V by I. Okay, you should be able to please practice those. The peak power happens that you should be able to find out. There are some equations in the book there. This is the peak power, and once you can find out, the VCC, the saturation current, you can find out the current, peak current, you can find out, the RL, and from there you can find out this is the saturation voltage of the switch voltage there. You should be able to find out the peak current loss during the switching time. You can find out what is the power during this time there. This is VCC, the drop here, the peak current there, the switch current there, the VCC, this is like a 1 volt, and you should be able to find the peak current. This is the equation on the book there. Please review them. I think that's the end of it. Now I hope that it's going to help you to know about the general characteristic of the devices and how to turn it on and also turn it off, about these diodes, and also the transistors and the MOSFET. With this one, I think this is this. Let me um, let me go back to my